All right. I will try to focus on class and not say fireable things. So, yes, dear Lord Jesus, we thank you for this day, and I thank you for your many blessings. Help us to understand your creation a little bit more today, Lord. In your name I pray, Lord Jesus. Amen. All right. I derived something last class. You may recall we delved too deeply and we discovered a beast. Yes, you remember. The stress energy tensor. The most formidable object I have introduced in this course thus far. Here it is. Tij is epsilon sub naught. EI, EJ minus 1/2 E squared. That's the magnitude of E squared. Magnitude of E squared. Delta Ij, close parentheses. Same pattern for B. 1/mu0. Bi, Bj minus 1/2 Kronecker delta Ij B squared. Why did I put the B squared second and the E squared first? I don't know. That's what happened. Now, great. So that's the stress energy tensor. And we worked out that let's see, what did we learn about this? One of the things we learned was that the force per unit volume, little f, can be written as the sum over I and j equals 1 to 3 of partial I Tij, parentheses here, x hat j, although x hat j is constant, so there's really no danger in differentiating it. And then minus, interestingly, epsilon naught mu naught partial s partial t, right? Where, remember, we also have introduced of late the pointing vector, which is 1/mu0, the cross product of E and B, right? Pointing vector. All right. So, and then the force, right, is equal to the integral over the volume of the force per unit volume d tau, which we can work that out. It ends up being the integral over the boundary of V of the sum I and j equals 1, 2, 3 of Tij x hat j, parentheses on this character here, x hat I. I guess the parentheses probably belong over here. Oopsies. Dot dA vector minus epsilon naught mu naught total derivative of the integral of the pointing vector over the volume. Now I have an abbreviated notation for this. My slightly abbreviated notation for this, dropping the summation and just kind of like a, I got to get a new bag. So my handy dandy shorthand for what we just wrote, which I will use on occasion, is that this is equal to the integral over the boundary of t dA comma whatever, leave it blank, and then, well, nothing really changes on the other term, minus epsilon naught mu naught ddt of the integral of s d tau. All right. So what is this? Well, this is the total electromagnetic force in a volume due to the electric and magnetic fields, or if you like to refer to them collectively as the electromagnetic field. We could do that. This is the net force of the electromagnetic field on charges in some volume V. we can calculate this by calculating the time rate change of the integral of the Poynting vector over the volume, as well as doing this particular newfangled integration over the stress energy tensor. All right. Now, so an example.
Is that over V?
Oh yeah, this is over V. Thank you. All right. Yeah. So the example I will foolishly start down the garden path for here. And this is the one that's in Griffiths. So at least I know the answer. Determine net force on northern hemisphere of uniformly charged solid sphere radius r. All right, and it has with charge q. All right, so before we do much here, let us just review what is the electric and what's the magnetic field in this context, right? Let's just write those down because we know them, right? So like the story here, right, is that the electric field is equal to, you know, Q over 4 pi epsilon naught, right? R vector over R cubed, or if you like, we could, I mean, however you want to do it, R hat over R squared for R greater than R or equal to R, right? And what's the electric field inside? Remember how it goes? It's Q R divided by 4 pi epsilon naught big R squared, big R cubed, I guess it was, right? It's gotta be big R cubed. R hat. For 0 less than or equal to R, less than or equal to R, right? I know, I just happen to remember it's linear. We can derive these by applying Gauss's law to a Gaussian sphere inside, right? And so, I mean, we've worked it out before, but I'm pretty sure this has got to be the right formula because if you put in little r equal to big R, they match. And I also remember it was linear in the uniform case. Now, all right, what else here? R hat is equal to cos phi sine theta sine phi sine theta cosine theta, right? So we should also notice that. That's going to be relevant. We're trying to calculate, we're going to be doing this integral over the northern hemisphere, right? So we have up here, in case 1, we have dA equal to r squared sine, oh, curse you, calculus 3. What goes there? Help me out. Theta? D theta, d phi, right? And that's in the r hat direction. But on the other hand, down here, in case 2, right, on this, there's two pieces, right? There's the bowl, upside down bowl, that's the top of the hemisphere, and then there's the disk, because we're calculating the net force on the upper hemisphere, and so there's those two pieces, right? So down here, dA is just, you know, golly. I suppose you could write it. I don't know if I should use. Well, I'm debating which letters are best to use down here. I'm kind of inclined to do S, ds, d phi, and then minus z hat. To me, that feels most natural. Just if you like, you could do dx dy, you know, if you prefer. But it's the downward pointing, right? All right. So then, as we think about this, common sense says it's fairly clear. It's fairly clear. Net force is where? Z direction, right? So like we don't need to calculate the stress energy integral in the x and the y. That's going to work out to 0 by the symmetry of the problem, right? Oh.
Could it have a twisting?
Well, no. I mean, but the electric field is radial.
I mean, magnetic.
There is no magnetic field.
Not true.
So, yes. But yeah, I mean, I hear you. Maybe I assigned you guys a homework problem with a non-zero magnetic field. Wouldn't that be exciting? I'm not sure what I did. Did I? But I think I left those, like, I may have left the, you can skip 2 problems in there because, why'd I do that? That reduces your suffering significantly. What am I doing? All right, FZ. I'm not giving you the full experience. All right, FZ is the integral over the boundary of V, right? And then, all right, look at it. This is the sum I equals 1, 2, 3 of T I3 x hat I dot dA. That's what I'm up against. If you look at, now how did I mean, do you guys see that what I'm doing there? To pick out the Z direction, it's about the J. J has to be 3 in that formula over there, right? The J is 3. That gives me the x hat 3. That's the Z part. So that's how I select the component. All right, and let me just write this out in stupid gory detail. This is the integral over the boundary of V of T 1, 3 x hat 1 dot dA plus T 2, 3 x hat 2 dot dA, right, plus T 3, 3 x hat 3 dot dA. So that's what we're up against, but of course there are 2 cases, right? Right, there are 2 cases. Now, notice something that's kind here. For the disk, only one of these survives. See, because dA is in the z hat direction, right? So like we have basically the integral over disk of, which one's, just the last one, right? T33 x hat 3. I won't try to simplify it, I'll just say it like that, right? And then plus you have the integral over the you know, the hemisphere, I'll call it H for hemisphere, of all of that jazz. All right. So, what are those? Here we go. T13 is epsilon naught E1, E3. T23 is epsilon naught E2, E3. T33 is epsilon naught E3 squared minus 1/2 of E1 squared plus E2 squared plus E3 squared, which makes T33 actually equal to epsilon naught over 2 times E3 squared minus E1 squared minus E2 squared. Now, what are those, though? Right? So, like, we're on the dome, where in the case r is greater than or equal to r, right? So basically, we need to use the inside field for the disk, but the outside field for the dome is how it happens. So the outside, so I'm currently thinking about the dome. So like T13 on the dome is, epsilon naught. All right, so E1 is Q over 4 pi epsilon naught. Well, we're going to have a Q over 4 pi epsilon naught 2 times, right? So let's just square that thing and leave it out front. Now E1, I'll write it out symbolically. It's going to be, x divided by what? R squared, right? Excuse me. Let me trade this formula for like my favorite one, which is r over r cubed. I just think that's easier to think through.
You want to use cosine phi sine.
What's that?
You don't want to use cosine phi sine.
Well, I'll do that next. One step at a time here. Just easier for me to process. But yes, I will do what you're saying, but it'll be the next step. So this one is z over r cubed, right? And as you told me, that's really epsilon naught q over 4 pi epsilon naught squared. And that is, so we get a cosine phi, sine theta, and then just a cosine theta, all divided by r to the 4th as it happens. And then this is epsilon naught q over 4 pi epsilon naught squared. And the E2, I'll just get straight to it's sine phi, sine theta. E3 gives me that cosine theta. And I'm again divide by r to the 4th, right? This is, okay, whatever happens here, all right? Yeah. I guess we could work it out. Fine. Epsilon naught over 2. And all of these pick up my q over 4 pi epsilon naught squared. And we're going to end up with a 1 over r to the 4th again, right? By dimensional reasons, it has to be there. And that's going to give me cosine squared theta minus sine squared theta, cosine squared phi minus sine squared theta, sine squared phi, so much suffering. All right, so that, of course, simplifies down a bit. we've got epsilon naught over 2 q over 4 pi epsilon naught. I guess I could put the r squared inside here just to be weird. Squared. And then that's going to give us cosine squared theta minus sine squared theta, right? Yay. But sadly, that's not all there is. See, because then we have the integral. Let me call this thing here Pac-Man, all right? So that is the integral over the upper hemisphere, right? And there is that stupid factor of epsilon naught q over 4 pi epsilon naught r squared, quantity squared. That's everywhere. Let's just pull that stupid thing out front. Integral over h. All right, so now we need to take the dot product of the dA. Oh, phooey. Well, this dA is r squared. Golly. R squared d theta d phi, and then we've got like cosine phi sine squared theta, sine phi sine squared theta, and then cosine theta sine theta. There's my dA formula. You need to figure out what's like the x, y, and z components of that contraption, right? So that right there, I use to actually do that calculation over here, like my x1 dot dA. So I have T13, which is, goodness gracious, cosine phi sine theta cosine theta times what? x1 dot dA, which apparently is r squared. What do I got? Cosine phi sine squared theta. I've got another r squared over there, but you know what? There's going to be an r squared everywhere. Let's just put that out here. Okay? I'm putting that out there. So, which I just said I'm putting it out there, so out there. So I got that, and then, d theta d phi, right? That's just the first term. Then plus what? Plus sine phi, sine theta, cosine theta, times my second component in dA, which is what? Sine phi sine squared theta d theta d phi. And then the z component, which is 1/2, don't forget the half, cosine squared theta minus sine squared theta. Sorry. Cosine theta, sine theta. Let me erase the d theta, d phi everywhere and just put it once out here. All of that just to find the contribution from the upper half. So yeah, do that integral. Where obviously, what's the deal? Theta ranges from what? 0 less than or equal to theta less than or equal to, pi over 2. And the phi ranges 2 pi. Rats, that's a cosine squared phi, that's no help. Sine squared phi, that's no help. Nothing here is 0. all right? And then we still have to do this piece over here, right? How would this look? What's T33 there? So T33 there, we would use the inside field for that one, right? So, all right. I can rewrite this as r squared. No. Oh, that's not good. Yeah, I just want, you're right. So yeah, let me just do, thank you. So I can just use that, right? I mean, that's the r hat. Well, okay, but fair enough. So, oh, I keep losing, I'm losing the, but that's the annoying thing is T33 is epsilon naught, right? E3, yeah, it's epsilon naught over 2. E3 squared minus E1 squared minus E2 squared, right? And then I have to do that. Then the x3 dot dA, which is just basically going to be, let's just say minus dA, if you'll allow me that notation. Now here, these are like, for instance, E1 is, you know, like, goodness gracious, Q, what's that? Well, yeah, fine, QR over 4 pi epsilon naught r cubed times, what did you say, cosine phi sine theta, but be careful, phi equals to what here? Is that everything? Is that E1? Yeah, that's E1. Theta is pi over 2? All right, so that, now, how is S and R related? I mean, I guess S is equal to R since we're here. But well, that's what the R sine theta is, right? R is equal to S times sine theta, I think. So this is R, this is theta, this is theta. So S is equal to R sine theta. But that's what this is. So I could rewrite this as like QS cosine phi divided by 4 pi epsilon naught r cubed. All right, listen guys, I'm gonna bail if that's okay. You get the sense of it, right? I mean, I could easily spend the whole class to just finish working this out, and I think I've done enough that you can see what's involved in the calculation, right? We have to figure out what the fields are and, you know, plug them into the formula, basically, is all I'm saying. So maybe that takes you back to your other class, I guess. I don't know. No? But there's no numbers. It's just, so that's not, I'd have to add numbers and precision. Is that what's required? So, oh, so the answer, though, let me just tell you the answer. And so if you this is worked out in Griffiths, sort of. I think it is. And he eventually finds that this integral works out to, after some effort, this works out to a rather satisfying answer, q squared over 4 pi epsilon naught times 8r squared. So that is the net force on the upper half of the hemispherical bolt. Now he calculates that in a different way earlier in the text, which is actually way easier. So the point of this example is just to say this is, I mean, part of the point of this example is why we don't do this. Because other means are easier to actually calculate the force, right? But that is theoretically what the stress energy tensor is telling us about. It's telling us about, you know, pressure and shear forces due to the electromagnetic force. So let me try to do some commentary here. So what I was actually trying to talk about today mostly is conservation laws, believe it or not. Maybe I'll be able to rescue it in the last 20 minutes here. I did intend to do this. This wasn't an accident. It's just I knew I wasn't going to get through it because I have been, well, Calculus 3 homework is due tomorrow, so I've been doing my Calculus 3 homework as that will happen. All right, so let's talk about, so first of all, in that calculation we just did, there was no Poynting vector because the magnetic field was 0. There's no Poynting vector to see there. So we only had to calculate this part to find the force. And it's interesting because it says that the total electromagnetic force can be understood in terms of two things, right? Like what the stress energy tensor does to the boundary of the region involved, and also the rate of change of the integral of the Poynting vector over the volume. And so at this point, I will remind you that you're taking another course called Classical Mechanics, where you learn, actually, we already know this from the previous course, that this is the rate of change of the mechanical momentum, right, with respect to time. And so the way to understand this, all right, is that this right here is the momentum, all right, momentum per time flowing through the boundary of V, right? And on the other hand, this right here is describing the change in momentum of the electromagnetic field's momentum, yeah. Very good. So it's helpful to define that kind of separately, right? And so he introduces a P. Let me write it down here. So P equal to epsilon naught mu naught times the integral over the volume of the Poynting vector d tau. This right here is the momentum in the electromagnetic field within the volume in question. And then he also introduces this G is equal to mu naught epsilon naught times S, right? And that is also epsilon naught times E cross B, all right? So this is yet another thing we're going to introduce. And he says what this is the momentum density. It's the momentum density within the electromagnetic field, all right? So, all right, if we're in empty space, thought experiment here. We're in empty space. What is the mechanical momentum? 0, right, empty space. dmech dt is equal to 0, right? So 0 has to be equal to the integral over the boundary of v of t dA, right? Minus the integral over, well, we just gave a name. That's what? That's you see that? That's just ddt of the integral of g d tau, right? And according to the notation that I introduced last class, we could also say, well, that's the integral over the divergence, quote unquote, divergence of the stress energy tensor. Here's Griffith's notation. I gave a different explicit formula for that last class, right? And that's partial g, partial t, d tau. But that holds for an arbitrary volume in free space, right? So that gives us the, let me write it up here. That gives us the, you know, the quote unquote divergence of the stress energy tensor has to be equal to the partial derivative of this g. Now, what was g again? G was the momentum density. So the divergence of the stress energy tensor has to do with, it has to be matched by the rate of change of the momentum density with time, right? So momentum diverges, it has to correspond to a change in the rate, change in the density of momentum. Now let me write down the formula for that thing. So this is yet another conservation law, right? How many conservation laws do we have in here? We got charge conservation, right? Last time, what did we find? We'll circle back to that in just a second here, but energy conservation, right? So nabla dot t, whatever that means, I'll tell you in just a second here, is equal to partial g, partial t. Now here, this contraption was defined to be the sum over I and j of partial I tij x hat j. That's the divergence of the stress energy tensor. And so what this expression that I just wrote down is, what it is, it's the local conservation of field momentum in the absence of charge. There is a local conservation of field momentum in the absence of charge. Now, so like going back to the formula on the left board, if we think about that, you know, there's if the oh no, I don't want to say that. I'm sorry, I'm getting off topic here. I need to number my notes. I foolishly not numbered them. Oh, here we are. All right. So yeah, we had this today. Last class we talked about the w dt, right, was equal to minus ddt of the integral over u d tau minus the integral over the boundary of v of s dot dA, right? Where the u was the, you know, that was epsilon naught over 2 e squared, right? Plus 1 over 2 mu naught b squared, right? This is the energy density. And so, and then of course you guys remember this was what? This has a name. What is this? Well, it is conservation of energy. That's true, I think. But this is a particular name. This is Poynting's theorem. Right. So it's saying that the rate of change of the energy in a volume and the energy which flows through the surface of that volume, right, they're related to the total change in the energy within the volume, right? Like if the energy in the electromagnetic field in a particular volume was not changing, that means that whatever I'm not saying this right. This is the work being done on charges within the volume, right? So if there's no work being done on the charges within the volume, then whatever change in the net energy of the electromagnetic fields in the volume, it has to be like balanced by the flow of energy through the boundary of that volume. We had an expression for this, like the local conservation. What was it? It was oh goodness gracious! I think it was what, partial U, partial T, plus, goodness gracious, I've forgotten already. The divergence of the Poynting vector is equal to 0. Is that right? Yeah. So that was local conservation of energy. All right. So what we have then, let's stop and notice something. Poynting vector, right? On the one hand, we can think of S as what? Energy per area time, right? If we calculate the integral of S dot dA, what's that give us? Over some surface, which I usually call S, so I'm at a loss. Yeah, this is is the power, right, of the electromagnetic fields going across the surface in question, right? Let's say through surface. Right, it's the energy per area time transported by the electromagnetic fields. It's an energy density, right? It's an area energy density. But you're right, it's not it's a power density, isn't it? Because it's energy per time. Or number two, we can think about mu naught epsilon naught S, right? Which was that was what we called G over there, right? Is equal to the momentum per unit volume, right, which is stored in the electromagnetic field. There's also a dual role to the stress energy tensor, right? Likewise. We can think of Tij as, giving, remember the formula F equal to what was it? The integral over, oh goodness gracious, have I forgotten already? Ooh. Boundary of V, T of dA, empty slot, right? And then there's the other term, I need to get glasses. All right, minus epsilon naught mu naught. Well, minus the integral over the volume of G d tau, right? Partial G, partial tau. I've forgotten. Partial G, partial tau. I guess we could write partial T d tau, right? But anyway, the larger point is that the stress energy tensor is giving us the pressure or the shear forces due to the electromagnetic field on some object, right? But also, number 2, Griffith says minus Tij gives the, as he says, the flow of momentum carried by the fields. Now, the way to understand these sentences is to go back to the formulas I've already said today, okay? So there's something kind of weird about that, right? Because I'm saying that the pointing vector says something about energy, but it also says something about momentum. Is that usually how energy and momentum works? Like kinetic energies, isn't it like p squared over 2m?
PV.
Oh, F, force times velocity, right? True, yeah. So I don't have this pinned down yet. Like, I didn't have enough time to like finish my thinking for today, but I feel like this can be connected to the formula that we saw maybe at the end of like physics 232, E equals PC. This relates the energy and the momentum for light, right? I think this is, we're starting to see some aspects of the fact that like light, in light, the momentum and the energy of the light, they're related. There's no mass. I mean, like, you know, we'll see in chapter 12 that if you have a massive particle, E is equal to m gamma c squared. Now gamma is a function of velocity and the speed of light, but there's nevertheless the rest mass there. But no mass for light. It's just this, which of course you can also rewrite in terms of frequency, like E equals hf. But anyway, I'm getting ahead of the story. So we now have local conservation of field momentum in the absence of charge. We talked about energy conservation within the field last time. If we study examples, if we ignore the momentum in the field, we can come to a seeming contradiction of the conservation of momentum, all right? Like, it seems like momentum's not conserved, but what's going on is that there's an interplay between the momentum, like the mechanical momentum in the system, and also the momentum in the fields. And these can be traded back and forth, right? The total momentum, it has to be a combination of like the momentum that's in the electromagnetic field as well as the momentum that's actually carried by massive charges that actually have physical momentum through their motion. Both of those two things have to go together in order to understand conservation of momentum. And he makes this explicit in the chapter by giving you, well, one of the examples that's truly mysterious is example 8.3. He has this long, coaxial cable, and he shows that with just a wire with a charge inside and with current flowing, he creates a situation where he has non-zero electric and magnetic field. The pointing vector is non-zero, and he calculates that like the net momentum in the fields is given by epsilon naught mu naught IV L z hat, right? And then, so there's nothing moving except for the charges in the wire, right? And this momentum is not the mechanical momentum of the charges moving. That would not explain this momentum, all right? It is the momentum of the electric magnetic field in this example. Then what he does in the example is he turns off he turns up the resistance so the current decreases. And when that happens, you get a changing electric field. And he describes how that then puts a force on the charge in the system, and then that force, if you integrate that force as the current drops to 0, you find that, what's the integral of force over time? Well, it's momentum, right? Change in momentum, impulse. You find that the impulse delivered by the force that's generated by the Faraday electric field, like the induced electric field, that is exactly matching the momentum which is in the field to start with before the current's reduced. That's a beautiful example, which we should go through. I'll do that next time, hopefully. And then in the next section, he talks about angular momentum. Angular momentum, where is my camera? Angular momentum, L, all right, is equal to R cross G. Now, I said angular momentum, but this is actually angular momentum density of electromagnetic field, right? It's a volume density, yeah? Just like G is a volume density. So we have 3 densities that are of interest. The angular momentum density, the momentum density, right? And also the last time we introduced the electromagnetic field energy density, U. Those are all volume densities. And then he explains that in order to conserve angular momentum of a problem where you have charges and currents, because we had that example earlier where we had nothing moving, and then we cut off the magnetic field and it made the ring spin. Remember that? Well, now we can explain how that happened by accounting for the angular momentum in the field, the electromagnetic field to start with. That angular momentum goes to 0, and it converts into the mechanical angular momentum of the ring spinning. Now, that's not the example which is in this section. What he does is he, again, looks at some sort of solenoid with some kind of thing wrapped around it, and as he decreases the current, the thing spins, and he's able to, again, account for the integral of the torque over time, giving the change in angular momentum, where that angular momentum was originally in the fields, it wasn't mechanical, but at the end of the process, it's mechanical. So only if we consider both the angular momentum in an electromagnetic field as well as the mechanical angular momentum can we give an account for conservation of angular momentum. But it is a bit of a mystery, the first example, like how it is that the field has momentum, because it's not like a time varying. It's like a steady current and a steady electric field, and yet it has momentum. It's kind of weird, honestly. And so that goes under the larger discussion of what's called hidden momentum. There's some kind of better answer, which is given in chapter 12 in terms of special relativity to explain the origin of hidden momentum. And then his last section in chapter 8 is on magnetic forces not doing work. But we already know that, so we can skip that section, as the examples in it would take me forever and a day to exposit. So they're good examples, don't get me wrong. But I am eager to get to chapter 9 where we start finding problems that we can actually calculate. Like, this stuff is beautiful, but it's also very hard to do an example in class that illustrates methods that you guys can learn in a reasonable time frame, right? But we do need to talk about the stress energy tensor because it completes the story of conservation laws. That's why it's here and why we're talking about it. So you say in mechanics, you just talk about the stress tensor, right?
Mechanics of materials.
Is it just the stress? Is it stress or stress energy?
It's just stress.
Just stress.
This, I think, is just the mechanical stress put on the
Right.
object by the field.
So you see the difference? This is stress energy because of this dual role. That's what's going on. That's the difference. That's what the stress energy tensor is versus just the stress tensor. Stress energy, because for light, for the which we'll soon learn is an electromagnetic field, there is a connection between energy and momentum, and as such, there's a connection between stress and energy. That's exactly the duality that's going on here. I'm being very fuzzy, but I'll try to be more precise next time. So thanks, guys.